So good afternoon to everyone. Again, my name is Domagoj Uremović. I'll be speaking about the algorithm for predicting crack path trajectory. The idea is to use topology optimization to increase the total fracture response of a structure by redistributing the second phase material within the domain. As always, initial conditions are some geometry, boundary conditions, loads. The question is where the crack goes. If we know it, we get a force displacement curve, and this knowledge can be used to calculate sensitivities for to use it in topology optimization. Algorithm that I developed is basically combine of three blocks. First is initial simulation with continuous domain, where the algorithm is able to find crack initialization. Then the biggest block is a bunch of small iterative simulations where each of them is this continuous domain with cohesive elements in use. And of course, if additional satisfaction of initiation criterion is satisfied, a new emerges. And then the final one with all open surfaces where cohesive elements are then implemented, we get the force displacement curve. Very briefly, we are using a mode one crack mode 1, and very briefly about cohesive elements. When we have a mesh, and if we know where we want to have them, let's say the midline, this one, we have to duplicate the nodes in terms of the IDs. So we duplicate nodes with the same coordinates. And then we assign them a new IDs, and existing elements, the ones over here, continuum elements, they have to be updated with duplicated nodes. And the last step would be to create cohesive elements. Cohesive elements were initially created for adhesive simulations, for simulations of adhesive joints. Then very soon they were updated as a zero thickness cohesive elements to model cracks. And this is the ones that I'm using. They don't seem as a zero thickness here just for the course of the presentation. Constitutive model used for a bulk material is elastic model in my simulations mostly. We tried also elastoplastic. It works nicely. And the one important for cohesive elements is traction separation law. The main characteristic is specific fracture energy. Elastic behavior in the beginning, which has to be at least one order of magnitude bigger than bulk material to avoid artificial compliance. Some damage initiation, which can be stress, strain, or something else as well. And softening, which can be linear, exponential, bilinear. We tried linear and exponential. Everything works nice. For the simplicity, we stick to linear. Both for initiation and propagation, criterion principal stresses are used with comparing it to maximal tensile stress of material. I didn't mention yet, we use this in ceramic materials used in metal production. And the idea is to use this method completely with topology optimization on slide gate plates. To get a precise crack trajectory, it would be very good to have the exact solution very close to the start of the softening. We can have this by kind of following the damage value in the first cohesive element, and then if this is the crack tip at the moment, next one will be this one, and the stresses in front of the crack tip will be in the elements aside. Okay. You will see that in the next slide, in the one after this one. So how it goes, we have a first simulation with some mesh. Now just engineeringly speaking, by the intuition, the stress will be dense over there. We will have our principal stresses, and through the principal stresses, we get the versor as well. And perpendicular to this versor, it's most logical that crack will go. It's not so visible over here, but there is a blue line over there, which shows us where the cohesive elements will be. And also 4 points on the sides, unfortunately not so visible. That helps us to always have quadrilateral element for the precision. And so for the next simulation, as you saw from the previous slide, the purple node is the next crack tip, and the one from before is actually an open surface in this simulation. In the next one, it will be 2 open surfaces and so on and so forth until we get the full crack response. On this trajectory now, we implement all cohesive elements again to get the force displacement curve. We tried this before, unfortunately it doesn't work. It's just a simulation of how does it go. Yeah, it's actually opening them, and since it's a quite brittle fracture, we don't see the elongation of the cohesive elements, which is actually happening. And just coming back to the precision again, ideally it would be very nice to get all the increments kind of going over there. I just put some points that are showing how we get increments of the finite element simulation across this track separation law. And this would be ideal scenario. Often it happens that they move on somewhere, and then principal stresses are actually introducing some error with their versor. So we get a zigzag pattern, and then the crack actually has a generally good direction, but with this zigzag. And to avoid that, and if we can, green point would be ideal for all the increments. We did that by using the subroutine. Simulations are done in Abacus, so and all the tailoring of the each simulation is done with MATLAB codes. And then we are actually following the damage in this Gauss points. When the damage actually starts, we reduce the time increment. And then when the second cohesive element in front of the crack tip, first Gauss point, goes above 90%, we kind of increase it again because we already passed and collected the stress density in front of the crack tip very precisely. And then when the next one is again above 90, we just simply stop simulation. And this approach helps us to reduce a huge time in computation and also post-processing, because each simulation is in this iterative phase is rather short. It's good to notice now here that the whole method is mesh dependent in this way, but actually mesh is from simulation to simulation tailored directly from the information about the principal stresses, and crack goes only for the element size, which and then the mesh is also reduced in this zone, which gives quite nice results. And as always in numerics, if we have nice computation results, mesh could be even lower, so even better precision. If we have this one, we get something like this in terms of increment on this track separation law, and then we get the dense results over there, and we can grab the correct one. So just an example. The gray zone underneath, just for connecting it to a framework of topology optimization, is a homogeneous material at the moment. So the crack goes pretty much straight in the middle. In some sequence of topology optimization, we get some more of a second phase material in the middle. So actually the crack goes a little bit aside. You can see this. This, let's say, jump, which is the cause of not perfectly fine-tune these values about reducing the time increment. Another example would be in the later phases of topology optimization. Several cracks are starting. Actually, the middle one is the one that can propagate the best. So the other ones are just stopping because increment in which first increment where some criterion satisfied is satisfied for this crack, so he goes on. And lastly, just another example. So you can see already over here that the algorithm is capable of seeing more than one crack, many of them, and actually also initiating crack somewhere in the domain, which is interesting. For example, in this case, crack started in the middle. Like this, then it came to this phase which has enhanced fracture properties. Then we have initiation in the bulk material on the soft side. So to be able for the crack to go on, it was natural that he goes first down to merge it and then to finish it. Therefore, the algorithm is also capable about to merge cracks, which is kind of intuitively also splitting. Splitting is this is a very last improvement that we did. So I didn't implement any splitting criterion, so I don't have any results about this, but it's quite ready. Just another remark is that in this framework of topology optimization, each element has its own properties because it's a combination of two materials. So the criterion is the same, but the threshold value is different. So for each element, it has to be a specific check. And thank you for your attention.